All right, so this is a good day today. We're going to go through, here's the plan. So, wow, we're missing quite a bit.
Let's go.
Are we?
All the time is
All right, so here's what I want to do today. We're going to talk about how we graph rational functions. And I want to do that by first kind of looking at how we graph polynomials and maybe even taking that one step further than we did. Okay, so our goal here, first of all, is let's graph this polynomial. And when I say graph, I mean sketch. We don't want to get an exact graph, we just want to get a sketch. We want to know where the x-intercepts are, we want to know what the end behavior is. As we go out to positive infinity and negative infinity to the left, we want to know what the behavior of the function is. So let's do a couple things with this. First of all, maybe let's factor it, right? So we can find the x-intercepts, find the real zeros. Okay, so what are we going to get if we factor f of x? What can we do first? First step in factoring. Pull out a negative x squared. Good. Okay, so we'll take out a negative x squared, which leaves us with what?
X squared minus 18 plus 18.
Okay. What else? Magic numbers. Okay, good. So we can reduce that then. To what? Okay. So then, what are my real zeros?
6 and 3.
6 and 3 and 0. Okay. So we get 0, 3, and 6 are places where y equals 0. So we're going to add those to our table, right? Our table's only got 2 rows. The x column and the y column. In calculus, we'll add more rows to the table. But these look like ordered pairs then, right? So those are the coordinates of the x-intercepts, right? So we can do some stuff then. We could actually, right away, we can start to, oops, I don't want to do that. Let me do, hang on, let me grab this guy.
Oh, that was the most, Kyle, that was the most sexual fight I have ever seen. You even ate it with your fingers, bro. You move him out. I could just see this. Kyle, you should invest in it. Down the loop. You have Christmas soy sauce again? No. That's what I'll call this. Soy sauce. What are you saying? Were you recording that first part?
I was.
Alright.
Okay, here we go. That's better. Okay, so what we can do right now, we can start to already make our sketch, right? We could go down and we could add some points. We got points at 0, 0, we got a point at 3, 0, and we got a point at 6, 0, right? So we know the function's gonna intersect the x-axis in those places. We just need to know what's happening everywhere else, right? So what's our strategy with the polynomial? What's one thing we can do? Seth?
Test the points in between the points.
Okay, good. So we can test points in between and maybe outside of those x-intercepts, right? Does that make sense? So we could pick test points, somewhere in there, somewhere in there, somewhere over there, and somewhere over there. And the only places the function can hit the x-axis are those three. So by knowing if it's above or below the x-axis in the other regions, separated by those x-intercepts, we can pretty much tell what this thing's going to do, right? Okay, so let's do that. So let's pick some test points. What if we pick
1.
Yeah, so we could let's pick some good ones. So we could pick like 1 would be an easy one to do, right? So we'll pick that as a test point. How about like 4? We could pick 10 and I don't know, -2, something like that. And we just want to know signs is all, right? So if we're going to check, let's just start with -2. F of -2 equals, and remember for this part, all we need to do, we don't need to figure out what the exact number is, we just need to know what the sign is. Here's where having it in factored form is really useful, because we can break this thing up into, we've just got 1, 2, 3 factors. We'll just figure out what the sign of each individual factor is at -2, and then find the sign of the products of those signs, right? So the first factor at -2 is going to be what? Negative. In fact, what's the sign of the first factor always going to be? It's got to be, right? Because x squared is always positive times -1 makes it negative, right? So we already know we're going to check the signs at all these places. And we already know that the first factor is going to be negative each time. Okay, at -2, what's the sign of the second factor? Negative. And the third factor? Negative. Okay, so the overall sign is negative.
It's called fuzzy math.
No, not really.
That's what Cooper called it.
It is?
Yeah.
Really? Huh. Okay, so, oops, wrong place. So that goes there, right? So we know that the function is going to be below the x-axis to the left of that x-intercept, right? And we do the same thing at 1. So at 1, we're going to get, what's the sign of our second factor at x equals 1? Negative. How about the third one? So that one is also negative. Okay? How about at 4? Negative, and the third one? For an overall sign of positive. Okay, and then finally at 10, we're going to get negative, positive, for an overall sign of negative. Okay, so it looks like that, right? Okay, so that already tells us pretty much everything we need to know, doesn't it? If we connect this, we make a polynomial out of this now. We know it's going to be below on this side. Now, polynomials, remember the leading term is the part that determines what the end behavior is going to be, right? So we already know it's below to the left of 0 and to the right of 6. What's another way we could look at that? Well, another way we could look at that would be to say, as x approaches plus or minus infinity. Okay, and this seems like a weird topic maybe, but we talk a lot about this in analysis. Like in calculus, we'll talk about this a lot. Really, we're kind of getting in, what I'm kind of doing here, honestly, is teaching this in a way where we'll be able to jump into this in calculus and it will make sense. okay? Because we're gonna jump right into these tables. You wouldn't really use this notation normally in an Algebra 2 class. And we're gonna talk a lot more about it in calculus. I'll have to do some proofs, and there's a lot more to a limit than what I'm saying right now. But for our purposes today, it actually works pretty well. The concept works pretty well. So as x approaches plus or minus infinity, think what that means. That means, graphically speaking, on the xy plane, as an ant were just to go infinitely far to the right along the function, what would happen? Now, you can't get to infinity, but you get the idea. If we just go without boundary to the right, what's the behavior of the function going to be? As we approach negative infinity, the ant is going along the function to the left without bound, going infinitely far. Okay, what's the behavior going to be? Well, as we do that, remember we did something earlier in the year, and I don't want to repeat it today, but see if you can remember. We looked at a function, and as we zoomed out, what happened with our polynomial? It started off looking like a line when we were zoomed in really close, and then we zoomed out a little bit, and it started to look like a parabola, right? It looked like a second degree term. Then it looked like a cubic, and eventually, if we zoomed all the way out, it kept going. It was a fourth degree polynomial. Didn't it look exactly like an x to the fourth function? Right? And the moral of the story was, in the limit, as we approach positive or negative infinity with a polynomial, the limit of the function is exactly equal to the limit of the leading term. The leading term is the dominant term in the function. Everything else becomes so small and insignificant that we only really care about the leading term, right? So when we're looking at end behavior, it makes it pretty simple. All we have to do is just focus there. Well, what does negative x to the fourth look like? What is, I mean, we looked at this also, just briefly, when we looked at our function toolkit. Real quick, if I were just to graph, like, for example, if I graph y equals x squared, that's just a parabola, right? If I graph y equals x cubed, it's a little different. Looks like that, right? If I graph y equals x to the fourth, well, it looks pretty parabolic. It's just going to be a little more squared off, but it's got the same end behavior, right? If I graph y equals x to the fifth, well, it's going to look pretty much like x cubed. It's just a little more squared off, but they're all going to be that way. It's just repetitive, right? The even ones are all going to look like modified parabolas, okay? And the odd ones are all going to look like these modified x cubed curves, right? Meaning that they have that gives us their end behavior. So for an even function, as x approaches infinity, what does y approach? Infinity, right? Goes up forever. For an even function, x squared, x to the fourth, x to the sixth, etc., as x approaches negative infinity, what does y approach? Infinity, right? Goes up forever. For an odd function, as x approaches infinity, y approaches infinity. But as x approaches negative infinity, f of x or y approaches negative infinity, right? Yes, sir?
Does that mean no matter what power it's 2, if it's approaching positive infinity, it's always going positive infinity?
Right, if the coefficient's positive, right, exactly. So then what happens in this case here? If we have f of x equals negative x to the fourth, what's it do to multiply an even power function by negative 1? What's that do to the graph? Yeah, it just flips it upside down. So now all that means is the tails, we call them the tails of the function at the right and the left, are both plunging down to negative infinity instead of going up to positive infinity, right? So we can see already here, we know what this answer is going to be. We know that the limit of the function is the limit of the power function in the leading term, right? Oh, how do I get a... Yeah, where did the 4 come from? That's not supposed to be there. Just x to the 4, right? That was confusing, sorry. And so the answer is negative infinity on both ends, right? So we already know, just from looking at the end behavior of that leading term, we know that the function is going to do, it's going to do this. When it goes through this point right here, it's got to just continue down forever, right? But the end behavior doesn't really tell us anything about what happens in there. right? That's where we gotta be a little more specific. Then we gotta be a little more introspective and analytical, and we gotta go to our table to see what happens close to home, close to the origin, okay? But out at the tails of the function, we already know what's gonna happen. Okay, so we know we've got our test points. That actually should resolve everything for us, right? If we know that the function's gonna be negative to the left of 0 and negative to the right of 0, well then what must the function be doing at that x-intercept? It's gotta be bouncing, but we should have known that too, shouldn't we? Because if we look at our factors, what do you notice about the x squared factor? It's squared, right? So it's a bounce, right? It's got, the x squared has a multiplicity of 2, and so that one we know it doesn't cut through like a line, it's gonna bounce like a parabola. So we gotta go back and maybe modify this one just a little bit. And then it's negative in this region, so it's down here, and then it's gonna be positive here. That makes sense, it's just doing this. Well, it's just doing this, isn't it? That's our function. Yeah. Is it perfect? No, it's not. We don't really care about if it's perfect. We just, at this point, we just want to know what's the sketch look like. Where are the x-intercepts and what's the behavior in between? Now, when we get to calculus, our job gets a little bigger. When we get to calculus, we want to know what are the exact locations of the peaks and valleys, the relative extrema, relative maximum. This would be a relative maximum. That's a relative minimum. These two together, we'd say are relative maxima. That's the plural. And in calculus, we learn to find those things. We also learn to find some other interesting things like where does the concavity of the function change? Where does it change from being kind of bowl-shaped up to bowl-shaped down and things like that? So those are interesting points for us when we look at applications of these functions. Okay. All right, so now what we want to do today, we'll start to do, probably won't finish it.
Got a question.
Yeah.
If you go back up.
Yep.
So on the graph, it's x to the fourth. Why is the negative on that?
Okay, because of the negative. Because we're multiplying it by -1. Right, so x to the fourth goes up with the coefficient's negative, it's going to go down. Okay? All right. So next issue then is a rational function. How can we deal with a graph of a rational function? As you might expect, it's a little bit more complex, but maybe not a ton. And we're going to use the same approach, right? We just want to know where are the x-intercepts, what's the end behavior of the function, and then we got to be able to figure out what's going on in between all the x-intercepts. But there's one other little thing we have to deal with here that we didn't before. For a polynomial, what's the domain of the function? All real numbers, right? Polynomials are very well-behaved functions. There's no place where you have to ever exclude from the domain. It's always all real. So we can go from negative infinity to positive infinity. There's no values that we have to exclude. Okay? Is that the same thing here? No, we've already dealt with this a little bit, right? There's some values of x we have to exclude from the domain because we can't divide by 0. So what's clearly the first thing we want to do with this function, probably, this rational function? Factor it. Factor the top and factor the bottom. So on top, what can we factor out? -4. Leaving us with, okay, bottom factors into +2. Okay. Good. So then there are some values we have to exclude. What are the values that x cannot be? X can't equal 5 and x can't equal -2. Okay? So those are places, we want to put those down right away. Those are kind of red flags. You got to know what's going on at those places. So at -2 and +5, the function does not exist. Okay? Okay, so y is undefined. Okay? Are there any places where the function is equal to 0, where it would equal 0? Because now think about this. Where does a fraction is undefined where the bottom is 0, right? But a fraction is equal to 0 where the top is 0. 5 divided by 0 doesn't make any sense, right? That's an undefined concept. But what is 0 divided by 5? 0, okay? So we'd look for the zeros of the numerator. Well, where is the top equal to 0? 5. So normally we'd think of that as being an x-intercept, but what's the problem here? It's undefined at 5, so it can't be, right? The function does not exist there, so it can't be an x-intercept, okay? All right, so we'll get to that in very shortly. Let's think about the end behavior though first. So we're going to figure out, we'll figure out like what we're going to do here to test some points and kind of maybe what all this stuff means. Before we go there though, let's look at the end behavior issue. Okay, so I've got, before we looked at only the impact of the leading term. Because as x approaches positive or negative infinity, it's the leading term of a polynomial that becomes significant, right? So for this function here, as x approaches plus or minus infinity, what's the function doing? Well, the limit of f of x as x approaches plus or minus infinity would just be the limit of the ratio of the leading terms, right? In the top polynomial, the only term that matters is going to be the negative 4x. In the bottom polynomial, as x explodes, the only term that matters is the x squared. And so we can just look at the ratio of those two terms. What does that simplify to? What is negative 4x divided by x squared? Okay, so that's going to become the limit of negative 4 over x. Okay, now let's think about the behavior of that. If I've got a fraction that's got a negative 4 on top, and the bottom is an x, and x is approaching positive or negative infinity. Now what's happening to these fractions? If I start off with negative 4 divided by 1, that's negative 4. Negative 4 divided by 10 is 0.4. How about if I make it negative 4 divided by a million? Well, I don't care what it is it big or small? Very small. Negative 4 divided by a quadrillion. Really small, right? Negative 4 divided by a number that's approaching infinity. That fraction's approaching what value? Did everybody see that? 0, because the bottom is getting infinitely big. Think about the behavior of a fraction. If the top is staying the same, but the bottom is getting infinitely big, that drives the size of the fraction to 0, right? I'll prove that to you in calculus. I'll actually go through a little proof of why it works that way. It's not a hard proof, but for now, I don't want to take the time. You just take it on faith. It makes sense conceptually, doesn't it? Right? That if the bottom is more powerful than the top, has a bigger power of x than the top, as x goes to infinity, the bottom is going to explode infinitely faster than the top, which drives the fraction to 0. Okay? So what's that mean? As x approaches plus or minus infinity, the function, meaning y, has a limit of 0. What's the behavior of the function going to be then as the ant walks to the right forever, for example? What's his y value going to settle at? 0. How about if he goes to the left forever? 0. Okay, so we say then that the function has what's called a horizontal asymptote. And we can put that in there. Okay, the horizontal asymptote. So there's our horizontal asymptote. The horizontal asymptote is the line y equals 0. What's that mean? Infinitely far to the left, or the right, infinitely far to the left, the function is going to stick to that asymptote. It's going to approach that asymptote and kind of try to stick to it, right? But it doesn't tell us what's happening in here. It tells us about the end behavior. In the last example, the end behavior was really dramatic. In the last example, the end behavior was we're plunging down to negative infinity at both sides. This one's kind of more boring this time, but it's also can be useful to us. In this case, the end behavior is that the function is just going to end up sticking to these asymptotes. Okay, we've got to figure out what's going on in the middle. Okay, so let's explore this a little bit. What's going to happen as x approaches, these are the values that we can't have, right? What's going to happen as we approach a value of negative 2? Okay, let's take a limit and see what happens. Let's just explore this, and then we'll look at a graph of this and kind of make sure. We'll graph it on Desmos, and we'll see if our predictions are what actually happens. So the limit of negative 4 times x minus 5 over x minus 5 times x plus 2 as x approaches negative 2. Okay, well, as x approaches negative 2, what's that going to do? This is going to become a what? The x minus 5 is going to approach what value? X is, when we say x is approaching a value, we mean that the x is getting really close to that value. So as x approaches negative 2, it could be negative 1.99999 or negative 2.0001, which is getting really close to it. We can't actually pick that value because it's forbidden. But in math, when we want to take a limit, we just want to see what happens when we get really close to it, right? So if I get really close to it, I'm going to get negative 4 times negative 7 over negative 7 times, what's that going to be? What's that approaching? As x approaches negative 2, isn't that approaching a value of 0? That's forbidden, right? But it's going to be it's not actually 0. It's going to be just a number that's getting close to 0. It's a really small number, right? So it's actually not 0. It's just a number very close to 0. What's infinitely close to 0? Now think what the behavior of the function is going to be there. I'm going to get something like 28 on the top divided by what's negative 7 times a vanishingly small number? Basically 0, right? It's going to be a number that's very close to 0, right? So we end up with the overall behavior of this thing just being positive 28 divided by a really small number. What is 28 divided by a really small number? What's the size of that fraction? That's a really big number, isn't it? If I divide 28 by 0.00000001, I'm going to get like an enormous number, right? That make sense? So what is the result of this then? What's going on as we get closer and closer and closer to negative 2? The value of the function is just going to be exploding, right? And we don't know if it's going to be a really big positive or negative number at this point. We'll deal with that in calculus, right? But we know that it's going to be explosive, right? So that tells us then that at negative 2 we're getting what's called a vertical asymptote, right? The function is going to be sectioned off, and it's going to, as the ant walks towards negative 2 from the left or from the right, he's going to, we don't know which direction at this point, but he's going to go flying up to infinity, positive or negative infinity, right? There's like a big wall in the function there that's going to really change its behavior, okay? So we can add that. So we know that right here, is a vertical asymptote. So we'll add that to our picture. Okay, there it is. That tells us a lot. That tells us a lot, because we know that the function, like let's just say, we'll figure out in a little bit, is the function above or below the x-axis here. If it's above, we know it's going to do something like that. It tells us a lot about the behavior of the function. Okay. Now let's look at this other place. At this other place that we couldn't go, which is 5. Right? F of x, algebraically, if we look at f of x, those two factors would cancel, wouldn't they? Right? If I cancel those, I would end up with a simpler function. It would just be negative 4 over, if those cancel, x plus 2. Right? Okay, let's look at our function real quick. Let's just graph this thing. I want you to see something.
And then the backspace, so that highlighted it.
What did you graph?
I just hit shift and highlight it, yeah. Okay, so here's our function. Okay, what do you know? Notice we've got a vertical asymptote at -2, right? We were right on that, okay? If I test the value of this function at 5, what do you think I'm going to get? Undefined. Okay, so what that means is if we were going to be accurate with our graph here, Desmos doesn't do this, but there's one little point. If I were to trace along this thing, it's defined everywhere on the, not at the vertical asymptote obviously, but every place else on the graph it's defined except at x equals 5, there's what we call a hole in the function. There's one point that's missing. All the points around it are defined, but at 5, the function's undefined. If I put in a value very close to 5, like if I put in 5.00001, that's fine. It gives me back a value, right? But as soon as I try to put in the value 5, it knows that the function's undefined. So the way we represent that graphically, when we graph a function, we'd have to do something like this. At 5, we'd have to put a little open circle there telling us that there is, at that one point, there's a hole. That's missing, right? How big is that hole? Infinitely small, right? Could you fall through it? No, you couldn't, because it's infinitely small. But it's there, right? The ants we're dealing with, by the way, are point-like in size, so they could fall through.
You don't know how skinny I
Okay, now notice that's a lot different, though. That's a lot different than the asymptote. Isn't that weird? Right? This is really kind of a big deal. We got these two places where the function doesn't exist. One of them is this almost unnoticeable little hole. The other one is this massive vertical asymptote that changes everything, right? What's the difference? Can you tell me what's different about how come one of those is a vertical asymptote and one of them is just a wimpy little hole? -2 is the vertical asymptote. That's the 0 that's a negative, or that's a vertical asymptote, and 5 is the 0 that's a hole. Okay, I'll give you, what do you think?
When you plug the 5 in, what you do with the
Yeah, okay, yeah, it's different. It's different. Now look what happened when we canceled the x minus 5 factors. We created this other function that looks a lot simpler. Let's call it g of x, and let's look at the graph of that one. So if we graph g of x, equals, what was it, -4 over x plus 2, right? It's the same thing. Look at that. It totally, if I turn g of x off, look what happens. It exactly overlaps. I guess I got to move him over, don't I? It exactly overlaps with the red function, doesn't it? Is it exactly the same? Is there any point that's different on g of x than on f of x? 5. Okay, let's check 5. Oh, g of 5 exists. It's fine. G of 5 is there, right? So what did we do? This is pretty interesting. When we algebraically canceled out the x minus 5s, we changed the function. We filled in the hole. That's what we did, right? But it's a different function. It's not the same function. We have to call it something like g of x instead of f of x, right? Okay, so what we find then is that if we have a unique 0 of the denominator, meaning a 0 of the denominator that is not also a 0 of the numerator, like -2. -2 is a 0 of the bottom but not the top. That has to correspond to a vertical asymptote. If I have a shared 0 of the top and the bottom, like 5, that corresponds to a hole in the function. Okay? Make sense? So in our graph, we can recognize that right away. Now that we know the trick, we could have seen, just when this was in factored form, we know that these are both undefined, but we could have done something like, okay, at -2, I can see that that's a unique 0 of the bottom, and so that becomes a vertical asymptote. So we'll put a VA above the -2. And that tells us we know we're getting a dramatic vertical asymptote. Now over here, This one, the 5 was a shared 0, so that's just an innocuous little hole in the function, right? And, that tells us a lot. Okay, so now, we can go down here to our graph, and we're gonna do the same kind of thing we did before. Now we have no x-intercepts this time, right? There's no place where the function actually touches the x-intercept, or touches the x-axis, okay? But we had these other places. We had an undefined function at -2, and we had a hole at 5, right? So all we gotta do now is we just have to figure out, we're gonna play our little trick with the factors, and we just wanna figure out, well, what's the sign of the function gonna be around those places, and that's gonna dictate what the function does, okay? So we're gonna go up here, we're gonna have to pick these test points again. So we'll pick one to the left of the vertical asymptote, so let's just pick one out here at like -10. We could pick one at 0 in between, that's a convenient one. And then up here, we could pick one at like 10. Okay, and we're just gonna play the same game we did before. We'll go up to our factored version of the function, and we'll just figure out what the overall sign's gonna be. So if I plug in -10, I'm gonna need to erase some stuff here. Just erase all this. Okay, so what do we get? What is f of -10? I'm going to get, on the top, I get -4, which is always negative, times negative, right? Divided by negative times negative. So then, we got to figure out what's the overall sign at the top. Positive, and the bottom. Positive divided by positive is always positive, okay? So we got a positive function there, okay? So that tells us already, we kind of know what's going on then. We know that the function's doing this, right? That's the behavior, okay? How about at 0? At 0, I'm going to get negative times negative over negative times positive, no, at 0, positive, which gives us positive over negative, so the overall sign is negative. Okay, how about at 10? Space again. What's that? Let's see if we can just figure out what the overall sign of the top is going to be at 10. I'm going to get negative times positive, which is negative, divided by positive times positive, so it's negative. Okay, that's everything we need to know, right? We know that the function's going to be below the x-axis over here the whole time. If we want to know where the hole actually is, well, what would we do? Well, we could plug it into, when we cancel the 5s out, this is a good trick. And this is, once again, this is kind of like a deeper calculus concept. But this is how if we tried to take this limit as x approached 0, or x approached 5, we would have gotten an answer of 0 over 0, right? Well, 0 over 5 we understand. That equals 0, right? 5 over 0 we sort of understand, because that's a vertical asymptote. What the heck is 0 over 0? That's actually what we call an indeterminate form in calculus. It means we have to do some more work to figure it out. And the more work that we would do is we would cancel those factors and create a new function that fills in the hole and just see what the value of that function is at 5. If I plug 5 in there, I get -4 over 7. And so, I mean, this is way above. I'm not going to ever test you on this year, but just so you can kind of get an idea of what we're doing in future years. At 5, the hole that we're filling in would be at the point 5, what did we say it was, -4/7? So if you want to get a really accurate estimate of where that hole is, that's where it would be. Do we care about that this year? No, we don't. But we can do the function, right? We know that it's negative the whole time, so it has to be doing that. Okay? And we do know, but we do have to add that there is a hole at 5. That's our graph of our function. Yep.
So isn't 0 also horizontal?
It is. We get a horizontal asymptote because of this right here, okay, that's important, because our limit as x approaches plus or minus infinity is 0, our horizontal asymptote is the line y equals 0. Okay, and we want to kind of put that on our, when we compile all our data here, we want to write the equation of the horizontal asymptote, but really we get it right here. Okay, the limit as x approaches negative infinity is 0. The limit of the function as x approaches infinity is y equals 0. So that's telling us that we've got a horizontal asymptote at y equals 0. Okay? So there's the equation of our horizontal asymptote. What's the equation of our vertical asymptote? X equals negative 2. Right? Okay, get the idea? Yeah, it's a lot of stuff. But it's pretty amazing what we're able to do then. I mean, we can get an accurate sketch of that graph. It's a pretty crazy looking graph just by knowing, where the asymptotes are. The asymptotes, when you get to the next level, kind of when we do a lot of this in calculus, you kind of think about the asymptotes as being the skeleton of the function. You can define the asymptotes, then you pretty much have an idea what the function has to do. You can fill in all the particulars by doing calculus. All right, we're out here at 25. Okay, we'll look at one or two more of these tomorrow. I got a couple little tweaks on the assignment, so that probably won't be available till tomorrow anyway.
Oh my God.
I got my sin there.